Hello all, welcome back to Predictive Analytics Regression and Classification course. We are going to talk about predictive analytics, regression and classification for lecture 14, and in this lecture we are going to talk about today natural exponential family. So natural exponential family is a class of distributions. Suppose you have bunch of random variables y1, y2, yn. They are independent observations, and yi has a density of the form something called natural exponential family, and this family, this density of which can be cast into this functional form. And I'll talk about what is this functional form and how can we cast into this form. Now question is, why should we study natural exponential family? Why we want to study natural exponential family? So if you look into any data set, okay, and this data set will have different kinds of variables, okay, so bunch of different variables, and pretty much you can classify these variables into certain categories. First category will be a bunch of continuous variables. Then second category will be bunch of discrete variable or discrete binary variable like 0 1 kind of thing, and third will be count variable, okay, count variables. Okay, so continuous variables will be like, income, okay, and maybe height, some measures, it is going to measure something. That is a feature of, typically if a variable is coming out of a measurement, then it is typically a continuous variable. If it's like some kind of action decision, here I'm going north or south, I'm going to going or not, yes, no, then it comes a binary or discrete 0 1 kind of variable. And sometimes it is, if it is count variable, then like, if the variable is coming out of a counting process, number of tumor, number of goals, or something like that, or number of courses you want to take, something like that. So now typically, how can you model income, height, this continuous variable? The models that the ones which models the continuous variable, they are typically like Gaussian distribution, then there are gamma distributions, then there are log Gaussian distributions. So bunch of distributions comes into this play. For binary or discrete, you have typically Bernoulli distributions, or typically we call it binomial family of distributions. And the count variables, typically we model with either Poisson distributions, negative binomial distributions. So these are the typical popular distributions which we use to model the count variables. Okay, the fourth category, there is a fourth category, I would say, called multi-class or multi-level variables, multi-class or multi-level distribution. multi-level variables. Okay. Now, what is the example of multi-class or multi-level variables? Suppose you are asking your subject, is it a bad or average or good service? Okay, so some kind of multi-level variable, a multi-class variable. Or how was the performance of a student? Is it a A grade? Is it a B grade? Is it a C grade? Is it a D grade? So what is the performance of a student, right? So grade could be a multi-level variable. Okay, so for that kind of variable we can have an interesting distribution called multinomial distribution. Okay, so we call it multinomial distribution. Okay, now all these distribution, Gaussian, gamma, Bernoulli binomial, Poisson negative binomial, multinomial distribution, all these distributions falls in the big family of exponential class of family. So if we can build a model, a predictive model where for exponential class of family, then automatically all other models will become a special case for this model, and that is where natural exponential family is going to play a very crucial role. Okay, so the first model I'm going to talk about binomial distributions. Suppose y1, y2, yn are binomial distribution with some m and theta I. Okay, now that means my distribution is f of yi theta I, choose mc yi theta I to the power yi 1 minus theta I to the power m minus yi. Now I can write this. This is the simple PMF of binomial distribution. I can write the same BMF in a slightly differently. I can write it as theta to the power theta by 1 minus theta to the power yi and 1 minus theta times to the power m. Now you see this part does not involve any y. Okay, and then this entire thing I can raise to e to the power log. So I can write a p as e to the power log p. I can write it in this way. So I can write this guy as e to the power log of the entire thing, and then log of theta 1 minus theta to the power y 1 minus theta to the power m. This entire thing I can write as log of y times log of theta 1 minus theta plus m times log of 1 minus theta. Okay, and then if I have a minus y here, e to the power, this is it like this, then you can write it in this way. So then you can write this part as h of y, this part as eta theta I, and this part as psi theta I. So you can put this in this format. Now if you go back, this binomial distribution function, the PMF of binomial distribution function can be formed in this kind of cast into the natural exponential family, with each part has its own functional form. Okay. Now next, you see if you Poisson distribution. If you see Poisson distribution, similarly you can write Poisson. This is the PMF of Poisson distribution. Okay, PMF of Poisson distribution, and I can write it in this format, and this log theta is my eta theta, this yi is my t of y, psi theta is, this theta is my psi of theta, and 1 over y is my h of y. So now this I can write it as I can say that Poisson distribution is a special case of natural exponential family class of distributions. Similarly, you can choose normal distribution. Suppose normal theta y1, y2, yn follow normal theta I sigma square, where sigma square is known. I'm just taking it as, and then you can write, this is the PDF of normal distribution, PDF of Gaussian or normal distribution. You can take the PDF and you can write it in this format, okay, and then h of y, this guy is my h of y, theta I is this, yi is this, and theta I square by 2 sigma square, there must be sigma square, is my psi theta I. So I can now say Gaussian distribution is a special case of normal natural exponential family of distributions. So now if I build a predictive model based on natural exponential family, that will be called generalized linear models, and this will work for any kind of response. If your response is binary, if your response is continuous, and if your response is count, everything will work. That's an interesting point. If your response is binary, then it must be a classification problem. So if your response is binary, then it is a classification problem, right? Then it's a binary classification problem. And if your response is continuous, then it's a regression problem, correct? We knew so far in machine learning they treat separately, but in statistics they all fall into the same problem, class of problem called generalized linear model, because binary classification and regression, they all fall in the same class of natural exponential family. Hence any predictive model based on the natural exponential family will be simply called as generalized linear models. Okay, so now what we are doing is very simple. We have a random component yi, because the generalized linear model will have 3 components: random component, link function, and systematic component. So yi follows some distribution natural exponential family, and link function, so this eta theta I is typically called the canonical form, eta theta I equal to zi, and zi equal to xi transpose beta. That's how we write the generalized linear model. And sometimes we just simply write it in this way, eta equal to xi transpose beta. Okay, now regression with GLM is simply, you just say y equal to normal theta I sigma square, and then theta I equal to xi transpose beta. It's called identity link. Simple, very simple. That's how a simple regression works in GLM framework. So simple regression is special case of simple regression. Simple regression is special case of GLM. Okay. Now count regression, all you have to do that, okay, y follow Poisson theta I, then you write it in this format, and that, okay, then eta theta I is log theta I, so we just say log theta I equal to xi transpose beta. That's it. So count regression or Poisson regression is also special case of GLM or generalized linear model. Poisson regression is also special case of GLM. Then classification, binary classification. Well, if a yi follow binomial 1 theta I or Bernoulli theta, then you can write it in this format, and this is your canonical form. So log theta I by 1 by theta I equal to xi transpose beta, and damn, simple binary classification is now binary classification is special case of GLM. Okay. So now all you have to do, you can define each function of the natural exponential family separate. Okay, like when you go back to the natural exponential family, the way you define it. So hy, eta theta, ty and psi theta, each of them you define as a separate function in your program. Okay, and now if you just go here, come here and define it as a negative log likelihood in that, and then where theta I equal to eta inverse xi transpose beta, and then just optimize it and you get the beta hat MLE. That's it. So the implementation is very simple in GLM. In R there is a stats package GLM, and you call family as Gaussian, link equal to identity. If it is a classification problem with logistic regression, then you call family equal to binomial with logit link. If it is Poisson regression, you call Poisson with log link. If it is Julia, in Julia there is a GLM package. Our CR raw packages also can handle all three models. With this we will stop here and we will do some hands-on with GLM. Thank you very much. See you soon.